Hi everyone, we're from Group 8, and in this video presentation, my group mates Tommy, Emerald, Kevin, Josephine, and myself, Wiagil, will present our case study on the vapor compression refrigeration cycle of the R633 refrigeration cycle demonstration unit. Alright, let's start.
In this part, I'm going to explain about background and literature review. There are two reasons why we chose to study about the refrigeration cycle. Refrigeration has been a major role in the field of industry, as it is being used as a method of preserving objects ever since the ancient civilization. The other reason is that by studying this, it aids us mechanical engineering students in understanding the fundamentals of engineering thermodynamics, heat transfer, and energy conversion systems. So let's get to the literature review. Refrigeration is the cooling of a system to lower or maintain its temperature below the ambient surrounding temperature. Refrigeration cycle itself is a thermodynamic cycle, which is a sequence of process that begins and ends at the same state, where the first and second law of thermodynamics is applied. As we all know, the most common refrigeration system in use today is vapor compression refrigeration system. In this diagram, it is shown that how heat transfer works in the refrigeration system in general. I'm not going to mention one by one what are the formulas, but there are some formulas that is needed to be used in order to analyze refrigeration cycle. But I can mention that the ones that are analyzed are the rate of heat transfer per unit mass of refrigerant flowing in the process of refrigeration cycle, the rate of power input per unit mass of refrigerant flowing, and what is the power input? It's the power input to the compressor, and then the rate of heat transfer from the refrigerant per unit mass of refrigerant flowing, and the last thing is the coefficient of performance of the vapor compression refrigeration system. It can be said that in general it is determined by the values of the enthalpy, as it is shown in the formulas. The values of enthalpy can be seen in the TS diagram, and the TS diagram can be described as following. Let's start from process 1 to 2S. So process 1 to 2S is isentropic compression of the refrigerant, or the refrigerant goes through the compressor with work being given to the compressor in order to compress the refrigerant to 2S. And then after that, from state 2S to state 3, the process that took place is heat transfer from the refrigerant through the condenser, and the refrigerant exits at a liquid state at state 3. And then from state 3 to state 4, it goes through the expansion valve, where throttling process takes place. And then from state 4 to state 1, heat transfer to the refrigerant through the evaporator occurs. And heat is transferred as Qn from cold region to the evaporator as refrigerant goes from state 4 to state 1. And from state 2S to 3, heat is transferred out from the condenser to the warm region and expressed as the Q dot out. So let's continue to LMTD. LMTD is a log mean temperature difference method, is being used in this calculation and analysis. So here's the formula. Delta TLM, LM is log mean, equals to F times delta TLM under counterflow conditions, whereas F is the correction factors that depends on the shape of the heat exchanger. F can be determined by seeing the table in accordance to the shape of the heat exchanger. And for your information, heat exchanger behavior is independent of the specific configuration, the configuration of the heat exchange itself. Lastly, determining the overall heat transfer coefficient is essential and the most uncertain part of any heat exchanger analysis. The overall heat transfer coefficient is defined in terms of the total thermal resistance to heat transfer between two fluids. As we can see here, these are the expressions that can be used to find overall heat transfer depending on the conditions.
For this project, our group has chosen to study the vapor compression refrigeration cycle demonstrated by this R633 unit. First, allow me to provide a brief explanation of the operational flow and components that make up the R633 unit with the aid of the schematic. So as we've mentioned, the R633 unit is a system that demonstrates the vapor compression refrigeration cycle. And in its cycle, the main components are compressor, condenser, expansion valve, and evaporator. But before we get into the main components' operational flow, let us first understand the presence of water flow here. So water is first pumped at a very high pressure from a water reservoir, and then it enters this water inlet and then travels to both directions, where it proceeds to enter a coil of copper tubes inside both the condenser and the evaporator respectively. And then it will leave the condenser and evaporator after performing its function, to be discharged back into the water reservoir previously. So what is the function of water? It is essentially the medium that allows the necessary latent heat transfer to or from the refrigerant in the evaporator and condenser, which completes the cycle of refrigeration. So now let's talk briefly of the main components' operational flow. But don't worry, our friend Tommy will provide a more thorough explanation later on. Firstly, the compressor will draw vapor refrigerant from the evaporator and begins to pressurize this vapor refrigerant. When this occurs, the pressure is increased, and when this happens, the temperature of the pressurized vapor refrigerant will also increase. After, this high pressure and high temperature refrigerant will leave the compressor and then enter the water-cooled condenser. By water-cooled condenser, we are talking about the coil carrying water, which absorbs the latent heat from the hot high-pressure vapor refrigerant, condensing it into the liquid state. This now hot high-pressure liquid refrigerant collects at the bottom of the condenser where it meets the expansion valve. The expansion valve is a float-operated needle that will discharge when the level of liquid refrigerant and the level of the float reaches equilibrium. When this happens, the hot high-pressure liquid is discharged through this tube. In this tube, the pressure will decrease to be equal to the pressure of the evaporator, and consequently, its temperature will decrease. This decrease in temperature must fall to the saturation temperature of the lower pressure. This reduction of temperature is accompanied by the formation of vapor bubbles, and this liquid-vapor mixture can be observed through the sight glass. So on entering the evaporator, the low-pressure liquid and vapor mixture, they separate. The liquid will enter into the refrigerant pool for evaporation, while the vapor will mix with the vapor produced by the boiling action of the water coils. See, evaporation occurs here due to the reduction of pressure as a result of initially the vapor being drawn by the compressor. And when vapor is drawn by the compressor, it causes the refrigerant pool to boil at lower temperature. The vapor mixture accumulated from boiling then returns to the compressor to repeat the cycle. There are other components that should be noted, namely the oil return capillary tube. This allows oil to be introduced to the compressor for controlled lubrication. And then we have pressure gauges to observe the condenser and evaporator pressures. So here are some of the unit's specification. It is designed to specifically operate on nothing but refrigerant R141B. And then the compressor used is a reciprocating and hermetic type compressor, which are commonly found in domestic refrigerators. It is also directly coupled to an electric motor having nominal power 810 watts. Here we can see that the condenser is of the water-cooled type, and evaporator is of the flooded type. This can be distinguished by the placement of the cooling coils.
Next, we move on to the operation procedure of the refrigeration system. The operating procedure of the refrigeration system will depend on the valve position. There are 5 valves in total for the system, and there are 4 main operations, which are normal operation, refrigerant pump down, oil return, and shutting down. And there are one more additional operation, which is air venting. The configuration of the valve for different operating conditions can be seen in the picture. In normal operation procedure, to start the unit, first we need to turn on the main supply and then turn on the cooling water supply. After that, we set the valve position to normal operation as seen in the picture before. By setting up the valve as instructed, it will allow vapor from evaporator to be drawn by the compressor into the condenser, and it will also allow condenser to return the condensed liquid back to the evaporator. Next, turn on the water supply so that water will enter the unit through the inlet. Thus, water supply will be separated into two flows. The first flow will enter the condenser, and the rest will be directed to the evaporator. The flow speed can be adjusted using the control valve in the flow meter. After the water starts flowing into respective condenser and evaporator, turn on the main switch so that the compressor will start and the cycle of refrigeration will begin. In the evaporator, the water will flow through a coil. While flowing in the coil, there will be heat transfer, which make water losses heat to the refrigerant. This will result in water temperature drop, and the refrigerant will boil and become vapor. This vapor will be drawn by the compressor into the condenser, while increasing its pressure and temperature, and will result in superheated vapor entering the condenser. Similar to the evaporator, the supply water will flow through a coil, and then the heat transfer will occur from the superheated vapor to the water. This will result in the rising temperature of the water, and also the vapor will change its state back to the liquid state. This condensed liquid will be transferred back to the evaporator through the expansion valve. When entering the expansion valve, the pressure of the condensed liquid will drop. This pressure drop causes some liquid to flash into vapor, resulting a mixed phase flow of the refrigerant to the evaporator. Next operation is refrigerant pump down. This procedure is often used to collect refrigerant in the condenser or liquid receiver. In this unit, the condenser and liquid receiver are combined in the same glass cylinder. By setting up the valve as seen in the picture before for refrigerant pump down, the flow of condensed liquid to the evaporator is blocked. So the refrigerant will accumulate it in the condenser and thus decrease the level and evaporation rate in evaporator. The liquid remaining in evaporator is mainly oil mist and refrigerant oil mixture from compressor. This oil cannot evaporate under evaporator pressure, and therefore it must be physically returned to compressor casing. Next operation is the oil return. Oil return should only be done after refrigerant pump down state has been achieved. With this configuration, oil may be returned to the compressor from the evaporator using the capillary tube. Once the oil returned to the compressor casing, the system may be returned back to normal operation. Then the unit may be either shut down or adjusted for further experiment. The last main operation is shutting down. In order to shut down the unit, it is suggested to pump down the refrigerant, then return it to normal running condition with the refrigerant accumulated in the condenser. When normal running condition is achieved, the main switch can be turned off to stop the compressor. After that, turn off the cooling water, followed by the water supply, and then finally the main supply. Once the unit has been turned off, set the valve to shutdown condition to prevent movement of refrigerant left in the evaporator back to the compressor. Next additional operation is the air venting. Air venting is achieved when the fan valve above the condenser is open. It has a function that allows air to exit into the void inside instrument panels. Air usually enters the system through the charging valve, then it will collect around the condenser coil. This air will act as an insulating barrier to vapor transfer, condensation, and heat transfer. So, unless to observe the effect of air in refrigeration system, it will be important to remove air from the system since air will disrupt the work of the condenser.
In the analysis section, I will be explaining the calculation of our study case on the refrigeration R633 unit. In this study case, we analyze the effects of increasing the condenser temperature on the heat discharged by the condenser and the impact of exposing the system to airflow. This table is the experimental data for analyzing the effects of increasing the condenser temperature. There are 10 data samples, 5 samples taken by the PA Hilton, and the other 5 is taken by Hasib Al-Mahbub. In this experiment, the system is isolated from airflow and the evaporator temperature is kept constant while the condenser temperature increases for each data. As a consequence, the increase in temperature also leads to the rise of condenser gauge pressure. From the table, we can see that the condenser water outlet temperature increases of each data. This is due to heat exchange through cross-flow from refrigerant fluid to coil. From this table, there are several parameters that we need to pay attention to, which are the heat exchange and the overall heat transfer coefficient at both evaporator and condenser. There isn't much information regarding the increase of condenser temperature with the coefficient of performance, since the data doesn't show positive relation in trend. However, the heat exchange and overall heat transfer coefficient at both evaporator and condenser decreases as the temperature of the condenser is increased. These phenomena occur due to the increase of temperature on the condenser, consequently increasing the condenser pressure. The rise of pressure decreases the volumetric efficiency and reduces the specific volume of the refrigerant gas. From this table, we are analyzing the effect of airflow on the system. When the system is exposed to air, the air will be swept towards the heat transfer surface, forming an insulating layer that reduces the heat transfer coefficient. This, in turn, drives up the temperature difference required for a given heat transfer rate, resulting in a higher refrigerant saturation temperature and pressure. As we can see, the data difference is relatively high when the system is exposed to airflow. We can see the heat exchange and overall heat transfer coefficient plummets when the system is exposed to airflow from this table. The coefficient of performance decreases significantly, and as a consequence, the total work required for the system also increases.
Based on the data and calculations shown previously, several graphs are made to better visualize the trends and the relationships between several properties. The first graph depicts the relationship between the rate of heat transfer and the condenser temperature. The blue line and dots represent the relationship for the condenser, while the red line and dots represent that of the evaporator. The graph on the top left is based on the data from PA Hilton, while the bottom graph is based on Hasib Al-Mahbub's data. It can be seen from both graphs that the trend for the graphs of the condenser is similar, that is, they both go down. However, there is a slight difference for the graphs of the evaporator. The values of the heat transfer rate is calculated from this temperature difference between the inlet and outlet temperatures of the evaporator. However, from PA Hilton's data, the values of inlet and outlet temperatures of the evaporator remain the same as the condenser temperature increases. This is why the heat transfer rate for the evaporator in the upper graph is horizontal. From these graphs, we can conclude that the heat transfer rate in the condenser tends to decrease as the condenser temperature increases, while in the evaporator, the heat transfer rate tends to increase. The next graphs show the relationship between the rate of heat transfer of both evaporator and condenser and the compression ratio. The compression ratio is the ratio between the pressure of condenser and the evaporator. Similar to the previous set of graphs, the anomaly here is the constant graph of the evaporator's rate of heat transfer. However, it can be referred to that the rate of heat transfer of the condenser tends to decrease with increasing compression ratio, while the rate of heat transfer of the evaporator tends to increase. Another variable that is depicted on the graphs is the overall heat transfer coefficient, symbolized as capital U. This graph shows its relationship to the condenser temperature, while the next set of graphs show the relationship to the compression ratio. Let us start with a set. We can see that there is an obvious difference between the data from the two authors. The overall heat transfer coefficient is directly proportional to the heat transfer rate. The values of heat transfer rate of evaporator from Mahbub are much larger than that from Hilton's, while the heat transfer rates of condenser from Mahbub are generally lower than Hilton's. This may explain why there is a difference in the graphs. However, the trends of both data are similar, that the heat transfer coefficient tend to decrease with increasing condensing temperatures. For this set of graphs, we compare the relationship of the heat transfer coefficient to the compression ratio from both authors. It can be seen from the graphs that they come to the same conclusion, that is, as the compression ratio increases, the heat transfer coefficient for both the condenser and evaporator tend to decrease.
So, according to our analysis, we've come to the conclusion that with increasing the condenser temperature, alongside its compression ratio, the overall heat transfer coefficient decreases. This consequently reduces the heat discharged from the condenser. We also concluded that the heat released by the condenser is dependent on whether the system is or isn't exposed to air. We found that the heat released from the condenser decreases with exposure to air and lowers the coefficient of performance. This indicates that there needs to be an increase in the total work done by the system. And that wraps up the presentation from Group 8. Thank you everyone for your attention and hope you learned something useful.